of it, which is threaded through a string, so it's hanging from the top. It's complicated, right? And there's a hook on the other side, which is attached to a string which drapes over a pulley, which is attached to a hanger, and you can put different masses on that hanger, and that hanger itself has mass too. So this looks complicated. What's the point? Well, when we unhook the hook that's attached to the string and the hanger, then we're left with, and I'll do a whole rundown lecture here in a second, but we're left with only three forces that are acting on that hanging bob. Those forces are the force due to gravity, which goes straight down, this tension force, which doesn't look like it goes straight upwards, okay? And also spring force, which points to the left. When you get this thing spinning, once you have it so it's not attached to the string and the hanging mass, when you get this thing spinning, now that mass, that bob mass, is moving in ideally uniform circular motion with some constant speed. So we know that there's a centripetal force that's acting on it. And what is the object that's causing the centripetal force? You tell me.
You can sit there.
Which part of this configuration is pulling the bob in the correct way to keep it going in a circle? Is it the tension in the top, or is it the spring pointing towards the center of the circle?
The spring.
It's the spring. So as we spin this faster and faster and make it go faster, we know that the centripetal acceleration is increasing. So that means that the spring force is increasing. Okay, so the spring starts to stretch, because when you stretch a spring, that means it's pulling on it. I'll go through all that. If you can spin it fast enough, then the string will hang straight up and down. And then the bob will just be going over a point that you've selected that you see. Maybe you take a little pen, you shouldn't mark with a pencil, but the point where the string is hanging straight up and down, that's the point where we're going to be doing our experiment, okay? So the goal today will be to spin this at some constant speed. That's a difficult part, okay? And then another member of your group is going to be counting how long does it take to go for a certain amount of revolutions, and from that data, and the data about how much mass is hanging over this in the first place, we're going to be able to try to prove Newton's second law. Okay, that's kind of like a little preview, but it should leave a lot of questions for you, and I'll try to answer them all right now. So let me put this back in here. Okay, so that's where we're going. How do we get there? Let's first talk about uniform circular motion. Once I can get this over. So we did a little derivation in the lecture class, but let's do it here just for everybody's reminder, and if we didn't have it in the lecture. So, uniform circular motion means that you have an object that's moving in a circular path with a constant radius, I mean that's a circle, and is moving at a constant speed. So maybe with a trajectory that looks something, I'm not going to be able to draw a perfect circle, but something like this. Okay, so that's that circle is tracing out the trajectory that mass, it could be a satellite or the Earth, or it could be the Earth or the Sun, if we're approximating as a circular orbit. Okay, that object is somewhere on that circular path at any given moment in time. So that means it's got a position as a function of time. It's got a position which is a vector. It's an arrow that points from the origin to where the object is located. So I'm going to call that r. And it changes as a function of time. And this is the angle as it's moving around that circle, which changes as a function of time. Like maybe it starts at 0 degrees, and then it clicks, it's at 90 degrees, and then blah, 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 180, then 270. So that angle, if it's moving at a constant speed, that angle should also be changing at a constant rate. And the rate of that change is what we're going to call the angular velocity. Call that omega. That's d theta dt. Okay? Just like velocity, translational velocity is dx dt. Okay? translational velocity is, yeah, go ahead.
Sorry, does that say r of t as like r parentheses t? Okay.
It says r as a function of time, that's right, because it's a position vector which changes. It doesn't change its length, but vectors have two properties. They have magnitude and direction. It's changing its direction the whole time. Click, 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 always pointing a different way in space. So it's a function of time. The omega, the angular velocity, okay, it's the change in theta as a function of time. Just the same way that velocity is the change in position as a function of time. So let's look at something really quick from our old geometry. If you have a little theta, or let's call it a little delta theta, and r, okay, and you're trying to calculate what is the arc length. Do you guys remember this? What's the arc length of a little piece of pie? If this is the change in the angle in that little piece of pie, delta theta, and this is the radius of that piece of pie from a circle, how do you calculate the arc length? Let's call it delta theta. Do you remember the formula to calculate the arc length? Calculate x pi.
Like,
Oh, what do you think?
like the arc length, right?
Yeah.
I was thinking 1 plus the derivative,
No,
like
it's
f of
a
x.
simpler, this is from like high school, middle
Oh.
school.
Theta, change in theta over 360 times r, 2 pi r.
Okay, sure. 2 pi r is the circumference, okay? So actually you got to the point I'm trying to make. So r times theta is how you calculate this. But only when theta is in what units?
Degrees.
No, radians.
Oh.
That's why you did the whole divided by 360, 2 pi thing. Okay, so r times delta theta is equal to delta x. That's only true, that relationship is only true if delta theta is in radians. Okay? Because how do you calculate the circumference? 2 pi times r, right? Not 360 times r. That doesn't give us the circumference. Okay? So why is that important? Because let's differentiate both sides. So if we make that a little tiny d theta, so r d theta is equal to dx, make it a little tiny little size of pi, that means that r d theta dt is equal to dx dt, which gives us that r times omega is equal to v. That's going to be really useful for us today in the lab, and also useful for us just when we talk about the centrifugal force, and when we get into torque also. But what you need to remember is that this is only true, this relationship is only true when the angular velocity is in radians. Radians per second, radians per minute, radians per hour. The time doesn't matter. But the degree unit is in radians. Okay, so let's write the position vector. Let's write the position vector as a function of time. It's got an x component and it's got a y component. How will I write the x component? If the magnitude of this vector is r, and that's theta, and we're going to call theta as a function of time, we'll call that omega times t. Okay, just in the same way that the change in length is v times t, the change in theta is omega times t. Okay. How do I write the, using trig functions, how do I write the x component of this vector? If this is a length r, and this is an angle omega t or theta, whatever you call it, how do I write the x component? Think trig functions, think components of vectors.
Cosine.
What's the x component?
R cosine theta.
R cosine theta, good, okay? So this has got a length of r, so this is going to be r times cosine of theta, omega t. What's the y component? What's the y component? R sine theta. But let's do something more interesting. What if we want to know what is the velocity of this thing that's going around in the circle, that we're going to be spinning around in the circle? Like how fast is it going? What do I do to the position function?
Derivative.
Yeah, derivative. So what's the derivative here?
Chain.
Is WT a constant?
It's omega, but
Oh, so is omega T a
omega is a
constant?
constant, but t is not. Omega is the rate that it's going around. That's a constant. T is not a constant. Omega is. Go ahead and think.
R sine T times W. I mean omega.
Yeah, exactly. So chain rule, exactly. You pull the omega out, so r omega, and then the cosine, derivative of cosine is negative sine. So negative r omega sine omega t. X hat. That's the x component of the velocity. What's the y component? Exactly. And then this is positive, so plus r omega cosine. Okay. That vector tells you the velocity, and you can check it. It's always going to be tangential to the path. So at this point in time, it's going to point this way. Okay, but when it's up here, it points this way. The magnitude. The magnitude is always the same, which we did this in our lecture class, but you can find the magnitude by taking the square root of the component squared, and you can see they both have r omega, so the r omega will come out, and then you've got sine squared plus cosine squared, so that's just 1. So the magnitude, the speed that's always the same, is r omega. That's constant because it's uniform circular motion. But remember, here we just derived the thing that I erased. Okay, that thing that I took, that we got from here, we just derived it from taking the derivative of this thing. Here it is again, v equals r omega. But remember, that's only true if that omega is in radians per second. Okay, so this is meters, and radians is really a unitless quantity. So this is meters times per second. So this is meters per second. That's why it gives us this v. If this was degrees, it'd be like meter degrees per second. That doesn't make any sense. Okay, so another way to write this. No, not yet. I don't want to rewrite that. So now let's get the acceleration. That's going to be the important part for today. How will we get the acceleration vector?
The derivative of d of t.
Derivative of v of t, exactly. The acceleration is the rate of change of your velocity. So here's the velocity. So we have to take the derivative of the velocity with respect to time. And here's the velocity. So what is that going to be? What happens there?
Negative r omega squared cosine omega t.
Ooh, wow, perfect. Negative r omega squared cosine omega t in the x hat direction. What's the y component?
It's r.
Good. Minus r omega squared sine omega t. Y hat direction. And you can play the same game that we played here to find what is the magnitude of that acceleration. That's a constant value. This is called the centripetal acceleration. Okay, so the magnitude, or what we'll call the centripetal acceleration, is going to be big for us today. You can take this component squared plus this component squared underneath the square root, and you can see they both have r omega squared, so that can come out. And then you'll have cosine squared plus sine squared, so that just becomes 1. So this is the magnitude, r omega squared. Or another way to write that, since we said that omega is v over r, is v squared over r. That's where that v squared over r comes from, that we just class. This is the one we're really going to use today. and just as a note, so that, which direction is that acceleration vector going? Notice that it's the same form, it's different size, but it's the same form as the position vector. Cosine x hat, sine y hat. But this is negative and this is positive. So it's flipped. Remember, when you multiply negative times a vector, you change its direction. So the centripetal acceleration vector always points for a circle, always points towards the center of the circle. And it's got a different size, it depends on how fast it's moving, but that's what we're going to explore today. In fact, the spring is the thing that's going to be giving it the centripetal acceleration. So that means that so the acceleration is due to a force. Where do I go from here? Okay. So another thing that we're going to measure today, well, what we're actually going to measure is not the angular frequency. We're going to measure the period. How long does it take for the bob to go around one time? But you'll actually measure how long does it take to go around 10 times and then divide by 10, so you get a nice average. So we're going to be measuring period. So that's literally in seconds. So the way that we're going to get there from omega is omega, which is, you can think of this as radians per second. We're going to deal with hertz today, so the little f. And that's cycles per second. That's how many times do you go around per second. So one full period for omega, since it's radians, is 2 pi. So we have to take omega and divide by 2 pi to get f. Okay? So one full time through, what I mean is f. I should really draw it. So if this is time, okay, to get from the beginning of a wave to the start of a true wave, that's 2 pi radians. Okay? That's also one complete cycle. Okay, so omega deals with radians, f deals with cycles. F counts how many times, omega counts how many radians. So I want to convert this to how many times, and I divide this by 2 pi. Because if this is 2 pi, 2 pi divided by 2 pi is 1. If I went through twice, this would be 4 pi. 4 pi divided by 2 pi is 2 times. Okay? So that's frequency in hertz. And then we're going to get period because if that's times per second, the inverse of that is seconds per time. Like how many seconds does it take for one time? So 1 over frequency is the period. This, along with something else, is what you're going to actually be measuring with the stopwatch. The stopwatch is going to give you a little t. You're going to divide by 10, and that's going to give you big T. So, now let's look at the experiment. And all these markers are diagonal. It's very frustrating. Hopefully we can get through it. So here is the device on the table. Here's the string attached to the hanging mast. Okay, so it's got 3 forces that are acting on it. It's got this little hanging mast, the bob. It's got the force due to gravity pointing down. It's got the spring force pointing to the left. And it's got the tension force pointing at some angle that's not perfectly straight when it's not attached to the string on the side. Mass of the bob times tension and the spring. What we want is to spin this device at a speed so that this guy moves outwards and the T is straight up and down with the mg so that they cancel out. So that the only force that's left over on this is sum of the forces once we're spinning in the right direction. Once we're spinning fast enough. So this guy goes like this, which is stretch the spring. Okay, so when it's like that, when it's spinning, the tension force and the gravity force cancel out, okay, because they're equal and opposite to each other now. And the only force that's left over is this, and that's the thing that's making it stay in a circle. So the sum of the forces in this condition, or I guess I should use this in blue, is that you know that this is only when it's spinning at the right speed. Then the sum of the forces are going to equal the centripetal force, which is the spring force, which is the mass of the bob times its acceleration. But its acceleration is the centripetal acceleration. So it's the mass of the bob times r omega squared. But omega is 2 pi times f. So this is n times r times omega squared. 4 pi squared f squared. Okay, so when this thing is spinning at the speed, at the only right speed, spin it too fast, it goes too far that way. Spin it too slow, it's too far this way. There's only one speed where this thing will hang exactly perfect, vertical. And in that case, the spring force is going to be equal to this. Okay? Now, we have to figure out what is the spring force equal to in that situation. So that's why we've got it connected to this other object, which is the string and the hanger. So when you have it connected to the string and the hanger, you can put just as much mass as you need on the hanger so that you get this up and down condition that you need. So you're going to control how many of these disc masses you put on there. So that when you've got this thing perfectly vertical, so that gravity points straight down, mass of the bob times g. Tension points straight up. The spring force points directly to the left, and this is the tension up, and this is the tension on the right. And you can do a free body diagram to show that the tension on the right, when this is stationary, must be equal, because this is the tension on the right, and this is the mass of the hanger times g. The tension on the right must be equal to the mass of the hanger times g. That means that when this thing is spinning at the right speed, the spring force is equal to the mass of the hanger times g, which you tested before you got it spinning. So you do kind of like two things for each setup. First, you figure out what is the spring force going to be to get you in the right motion. Then you take this string off and the hook off, and then you start spinning it until you get that vertical position, and you calculate you measure the time for 10 revolutions, and from that you're going to get the frequency. Okay, this is a pretty complicated lab, but I'll come around and help you. So we're almost there. So what I want you to plot is mass of the hanger times g versus frequency squared. So this is frequency 1 squared, this is frequency 2 squared, this is frequency 3 squared. Those are different experimental runs that you do. I think you do 5. Each time, you're going to need a different hanging mass to be able to get the string to be straight up and down, because each time you're going to take this hook here and you're going to thread it through a different hole in the ladder. Okay, so you're moving this thing farther and farther away from equilibrium, requiring more weight to pull it back, therefore a larger spring force. So the holes in the ladder here are the different runs that you're going to do. First, like the longest hole, the hole farthest away. Then you put it in and you do all the experiment. Then you do the second hole, and the third hole, and the fourth hole. Each time requiring more hanging mass to make the thing in equilibrium. I hope that makes sense. I think it makes sense in my head when I said it. This is mass 4 of the hanging thing times G block, etc. And you're going to get data points that look like this when you plot them in Excel. And there's going to be a slope, you know, like all of our experiments. This is the slope of this is your experimental value. Okay? You can plot it, you go in Excel, you find the slope, that's the experimental value. The theoretical value of hanging mass versus frequency squared is this. The mass of the bob times R. R is the distance from the center of the post to the center of the bob when it's perfectly straight. And that's going to be constant for all of your experiments. 4 pi squared times f squared. So this, if you're plotting this versus this value, that's a linear function with this as your slope. Okay? So this is the theory. So the goal then is to do a percent difference, which is the experimental value minus the theoretical value divided by the theoretical value times 100. Okay, so you know it's a weird experiment, but what will you need? You'll need to know the mass of the bob, so you'll have to weigh that. Bless you. Oh, there's scales in the middle here. Okay. You'll need to know the radius, which is some constant. So regardless of which hole you use in the ladder, when the bob mass is straight, it passes over a specific point. You should observe what that point is. That's the point that you're going to want always to pass over when it's spinning. Okay? The R is the length from the middle of the post to that location. Notice there's a G here. Okay? So that R, you have to convert it to meters if you're going to use 9.8 squared here. 4 pi squared. You get the F for each different hole that you use on the ladder. You have to use a different mass to get it straight, first of all. That's where you get this thing. Okay. But then when you start it spinning, one of your group members is going to click the stopwatch, and he's going to, or someone can count like how many spins there were, and when you get to 10, you stop it, and you look at the time, you divide by 10, that's going to be your little t. Or, yeah, that's going to be your little t. This is total time for 10 revolutions. T is little t divided by 10. And so you get F 1 over t. Okay, so that's how you're going to get your F's for that. Now, here's something that you're going to want to keep in mind from this stopwatch. What you should do is get it spinning so that it's at the right pace, because that's not easy to do. You don't want to spin it too fast, you want it to spin it too slow, you want it to stay spinning, which is pretty frictionless. It will spin with its momentum. It'll want to spin at a constant rate. So you just have to do a little bit to keep it going. Once it's going at the right pace, then kind of count backwards, like 3, 2, 1, 0. Like every time it passes over that point, go like 3, 2, 1, 0. When you hit 0, that's when you hit start. So it's 3, 2, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's 10 rotations. Don't go 1 to 10, because that'll only be 9. So count down 3, 2, 1, click it on 0, and then count to 10, and you'll be there. I think that's everything. I know it's still probably pretty confusing, but I'll be coming around to help. And also the lab manual will explain it also if you want to just read it. And then as you go down to Canvas, and you'll see the photo of the data sheet is a table that I want you to create with all the information that you need to take
this thing out.
and the calculations that you need to make. And then the lab report tells you what to do. I know this is a strange lab.
Yeah, that's
We got this.
Make sure that this should be calibrated. So there's more scales over here too, and there's more over here. Yes, good. So you need to add the hanger to the massive vector. You need to know how much it weighs. And you don't need to convert to kilograms. You can do everything in grams because that grams will cancel out.